This is section 7.3, solving linear systems by adding or subtracting. There are steps to use to solve linear equations by adding or subtracting, just like there are steps in the substitution method. Look at the steps below, and then we'll use them to solve a system. So here are the steps that you would normally follow. First, you would line up the equations so the variables line up or match, almost like when you were adding in second and third grade and lining up the hundreds and the tens. You want to line up the x's and the y's so that you can easily add or subtract them. In step 2, you do the adding or subtracting of the equations to eliminate one variable. You want one of the variables to actually disappear or be eliminated so that you're only left with one variable and you can solve for it. In step 3, you're going to solve the resulting equation for the other variable. That's the one that's left. So in other words, in step 2, if x was eliminated, you would be solving for y in step 3. In step 4, you're going to use the result from step 3, what y equals, for example, to substitute into either one of the original equations to find the value of the other variable. Make sure it's one of the originals that you haven't changed in any way, even moving it around, because you could have made a mistake doing that. So let's take a look at the first example. In the first example, we're going to solve by adding. The equations are already lined up so that the variables are lined up and are matching. In the first equation, we have 2x plus 3y equals 11. And in the second, it's minus 2x plus 5y equals 11. You can see they're already lined up. That's our step 1. So you can move on to step 2. We're going to add these two equations to eliminate one of the variables. When we add them together, we get 8y equals 24. So now that the x is eliminated, you can solve for y. You get y equals 3. We take y equals 3 and we substitute that back into either one of the original equations. So if I use the first equation, I have 2x plus 3y equals 11. So 2x plus 9, using 3 as y, equals 11. So 2x equals 2, or x equals 1. My answer then would be the point where these two lines intersect, and that would be 1, 3. We take the x-coordinate and the y-coordinate, and we show what point that would be. You should be able to substitute this result into both of the original equations to make sure it works. It's not one or the other. It should work in both equations, because remember, the point is on both lines. It's just where they intersect. In example 2, we're going to subtract. And we do it here because we have the same coefficients in front of the y. If we were to add them, we just have double the number of y's, right? We're not going to be eliminating a variable, but you want to eliminate one. So if you see that the same sign is in front of the coefficient of one of the variables, you want to subtract them. So we have 4x plus 3y equals 2, and 5x plus 3y equals negative 2. When you add these two equations together, you should get the opposite of x equals 4, or x equals negative 4. I believe this is a negative 5x. There we go. When you get x equals negative 4, we're going to substitute that back into either one of the original equations. I substituted it back in the first equation, so I have 4 times negative 4 plus 3y equals 2. Negative 16 plus 3y equals 2. So 3y equals 18, or y equals 6. So my answer then is negative 4, 6. The answer isn't x equals negative 4, y equals 6. Remember, these are coordinates of a point. So you put them in parentheses, negative 4, comma 6. And this is the point where the two lines intersect. Now here's an example when the terms are not lined up. So we have to switch around the order of the terms and change your equation a little bit. Sometimes they are in the wrong order. So this is using that first step, which we haven't had to worry about just yet. The first equation is 8x minus 4y equals 4. And the second is 4y equals 3x plus 14. You need to rewrite the second equation so it lines up with the first equation. So in other words, we want it to be x, then y, and then the constant on the other side. It's in standard form here. So the first equation remains the same. The second equation, we bring the 3x over to the left side, so it becomes negative 3x plus 4y equals 14. Now you can add them together because the y terms have a negative 4 and a positive 4 coefficient, and when you add them together, they're going to disappear. When we add this together, we get 5x equals 10. And when you divide by 5, you get x equals 2. You can substitute x equals 2 back into either one of the original equations and solve for y. So you get 8 times 2 minus 4y equals negative 4, or 16 minus 4y equals negative 4. Negative 4y equals negative 20, so y equals 5. Your answer then would be the point 2, 5. Now we're going to look at solving linear systems about rates and currents. All right, rate and current problems are a little bit difficult. They're sort of like mixture problems because when you're riding in a boat in some kind of body of water that has a current, the speed that the boat is going is reflective of the current strength. When you're going upstream, you're fighting the current, so the current is working against your speed. And when you're going downstream, the current is helping you and it's increasing your speed. So if we have a problem like this, you're going kayaking, you go upstream against the current for 12 miles and it takes you 3 hours. You go downstream with the current and it takes you 2 hours. What is the rate of speed of the kayak in still water, that is without any current, and what is the rate of the current itself? Well, the first thing you want to do here is find the rate of the kayak with the current, whether it's against it or for it. That's what's reflective in the information that they gave you. So you're going to use an equation you learned in Chapter 1, that's distance equals rate times time. When you're going upstream, the distance is 12. We don't know the rate, but we do know the time is 3 hours. So we know the rate is 4. That represents 4 miles per hour. Going downstream, you're going the same distance, the 12, but this time it's taking you 2 hours. See, the current's helping you, so it's not taking you as long. So this time your rate is 6 miles per hour. Now those rates include the current. We want how fast the boat is going in still water. So we're going to write a system of linear equations and make sure you identify which variables you're using for what here. Please define them or you're going to have difficulty answering the question at the end. I usually set x as the speed in still water and y as the speed of the current. Okay? If you use those two variables, then going upstream, x minus y, because going upstream the current's fighting you, so it's taking away from your speed. So x minus y equals 4, the rate that we calculated at the beginning. And going downstream, x plus y equals 6. See, now you have the help of the current. Downstream you're always adding, upstream you're always subtracting. Once you have these two equations, you can add them together to solve it. So you get x equals 5. Well, look back at your definition of the variables and you see that x is the speed in still water. So the speed is 5 miles per hour. If you know that x plus y equals 6, then you know y must equal 1. So the speed of the current is 1 mile per hour. So the answer to the problem is the speed of the kayak in still water is 5 miles per hour. The speed of the current is 1 mile per hour. Let's try another one like this. This is a riverboat, and a riverboat's traveling 28 miles upstream in 7 hours and 28 miles downstream in 5 hours. The speed of the current remains the same throughout the round trip. Find the average speed of the riverboat in still water and the speed of the current. The first thing we always do is find the speed that includes the current, whether you're fighting the current or you're riding on top of it. So we use distance equals rate times time. We know that upstream the distance is 28 miles, and that equals the time 7 times r, so r equals 4. Downstream we have the distance of 28, and that equals 5r. You took 5 hours for the trip, so r equals 28/5. If we set x equal to the speed of the riverboat in still water and y equal to the speed of the current, Then when you go upstream, x minus y, the speed of the boat minus the current equals 4, the actual rate that it traveled when you measured it or observed the boat. In the second one, we're going to look at downstream, and when you go downstream, the current's helping you, so x plus y equals 28/5. We're going to add the equations. That will eliminate the y's, and we can solve for x. So 2x equals 48/5. Remember, 4 is 25th. So x equals 48 divided by 10, or 4.8. So 4.8 miles per hour is the speed of the boat in still water. X is the speed of the boat in still water. Always look at how you define your variables. If x equals 4.8, then y must equal 0.8, right? Because we know x minus y equals 4 from that first equation. That's the speed of the current. These aren't difficult if you follow the same pattern every time. Calculate the rate with the current, whether it's fighting it or riding it. Then use x plus y and x minus y to reflect the upstream and downstream rates. And then you should be fine.